All right. So what happens if we do not have the correct number of unpaired electrons? Here's an issue. I want us to remember carbon's electron configuration. I know that was a long, long time ago. Carbon, for its orbital diagram, valence orbital diagram, we're only going to do the valence, remember, because those are the ones that are go into reactivity, go into bonding. Its valence looks like this: 2s2, 2p2. There's one electron in the 2px and one in the 2py. Now, how can we look at this quantum mechanical model of carbon atom and see any relationship into Vesper theory where carbon can make 2 or 3 or 4 bonds? When it makes 3 bonds, they're around 120. If we had 4 bonds, that's 109.5. What's happening? Because we know in reality, these are 90 degrees from each other, right? What we just talked about with sulfur. What happens is a hybridization. Now, because of the inconsistencies when we started viewing atoms and seeing the shapes that were occurring, Vesper theory was born. But then what happened was people and scientists were really baffled by the inconsistencies. And so it was postulated that valence atomic orbitals could hybridize before bonding took place. And so one hybridization of carbon is to mix the s's and the p orbitals. And what happens when we mix s's and p orbitals, even though these are all different energies, let's imagine throwing them all together, putting them into 4 equal energy orbitals, and one valence electron goes in each. What I like to compare this to is cupcakes. I hope we've all made cupcakes before. I hope we've been that lucky in our life to have made cupcakes, or at least seen cupcakes, maybe eaten a cupcake before. Now, cupcakes are made with sugar, flour, eggs, some sort of liquid, whether it's oil or water or butter. And we mix all of those very different things together. And when we mix them all together and we put them in equal little trays, we hybridize those ingredients. We are literally taking very different substances, mixing them all together to make perfect, identical cupcakes, hopefully perfectly identical. Now, that's hybridization. We take different atomic orbitals, mush them all together to come out with degenerate orbitals. Now, if we remember what the word degenerate means equal in energy. We are trying to make equal little cupcake orbitals for our central atoms. Now, when we look at this, what we want to be able to see is carbon does not bond as theorized with valence bond theory originally, or quantum mechanics. What it actually does is a tetrahedral when we have single bonds. So something must be happening to these valence electrons in order to get them to separate. We got to unpair and become equal in energy. All 4 of those bonds in CH4 are the same in terms of bond energy. And so something must happen to those atomic orbitals. And that is what we call hybridization. Hybridizing is mixing different orbital types to get a new set of degenerate orbitals. Now we can mix S's and P's and D's. Hybridization has not been noticed past those D orbitals, but notice here that there are a wide variety of combinations. SP contains 1 s orbital and 1 p orbital. Now that 1 is not the principal quantum number. We're talking physical orbitals that we've taken. sp2 would be an s orbital and 2 p's. sp3 is an s and 3 p's. sp3d You grab one more D, sp3d2, you grab two Ds instead of just one. Carbon can bond in any of these three ways. It can be sp, sp2, or sp3 hybridized, and that's what we're going to investigate today. How does it work? Well, the number of standard atomic orbitals is going to be equal to the number of hybrid orbitals. So if I need to make 4 bonds for carbon, I need to take 4 atomic orbitals, an s and 3 of those p's. Notice I counted all of the lines. I took an s, a p, and a p, and I hybridized them to make 1, 2, 3, 4 degenerate orbitals. Math has to work out. Whatever you put into the cupcakes, you get out of the cupcakes. And so if I put 4 atomic orbitals in, I will get 4 degenerate hybridized atomic orbitals out. Now, hydrogen cannot hybridize. It only has 1 valence electron and 1 valence shell. So that doesn't work. But what's great about hydrogen is it's usually not a central atom. Hybridization happens for the central atom only. And that's going to be very, very important for us to understand. If we look at a Lewis structure and identify a central atom, that atom can hybridize if required. Usually they do. Very rare occasions, like the H2S example, do we not see hybridization occur. The number and type of standard orbitals, again, determines the number and shape of the hybrid orbitals. So I took an s orbital, this one, and I took 1, 2, 3 p's. I'm going to have an orbital that's some combination of s, p, p, p. Now, that is about 25% s and 75% p. So what my shape tends to look like is kind of like a P with just one bloated lobe. And that's because that's what made it. So we take that s orbital, which is the sphere. We took the p orbital, which is the dumbbell, and we literally put them together and make some sort of a hybridized form. Now, when we look at what happens with that hybridized form, here's the s orbital, the px, the py, and the pz. Put them together and spread them all out equally because they're degenerate now, and that's where we get the tetrahedral. Yay! There's much rejoicing. That's where we can get the 109.5. Only way to understand how the tetrahedral is formed is through hybridization. We have to have equal energy orbitals in order to understand that. And so hybridization is our theory that predicts what we observe. So for the sp3 hybridization, it is literally going to be tied to the 4 electron group of Vesper theory. Whenever you have 4 electron groups, you're going to see that tetrahedral geometry. The bond angles are 109.5. That must mean that the actual atom in the center hybridized in an sp3 fashion. Notice the s, the p, and the p. Those are 4 atomic orbitals going to make 4 hybrid orbitals, which is 4 electron groups. Now, what we can do to just describe a little bit more about what's happening is we can actually figure out what orbitals are going into the overlapping themselves. So when we have single bonds are always going to be sigma bonds. You have to have that direct overlap first. So a sigma bond will be the direct overlap that occurs in every single covalent bonded pair of nonmetals. Specifically, what we can say is the carbon that is sp3 hybridized overlapped with the hydrogen that is s orbital. Hydrogen, again, doesn't hybridize. It's an outer atom. Outer atoms usually do not hybridize. When we look over here at the nitrogen, again, nitrogen is sp3 hybridized, and it's overlapping with a hydrogen in an s orbital. So we can say that is true for every single bond in these structures. Now, what about the 3-electron group? I have 2 examples here that I want to go through to be able to emphasize, well, is 4-electron groups the only thing that hybridizes? No, everything technically hybridizes. Let's look at these 3-electron group structures. Carbon's in the middle because he makes the most number of bonds. We've done this guy before, but let's just do him again. Carbon brings 4 electrons to the table. Oxygen brought 6. Each one of those hydrogens brought 1 electron. So therefore we have 12 electrons total. 2, 4, 6, 8, 10, 12. When I look at what my structure has given me, I would say, you know what? I don't want to put that as a lone pair. I want to go ahead and share one more pair so that carbon gets an octet. I ran out of electrons and I didn't have an octet for carbon. So this would be a 3-electron group structure. We would imagine that that is trigonal planar. Carbon has bond angles that are 120 degrees from each other. Again, carbon, well, what happened, dude? You had 2 s orbitals and the 2 p orbitals. If we were to fill those up to get its valence electrons, now we look at this carbon and say he looks different than the tetrahedral. So what happened? Well, in reality, we only needed 3 hybrid orbitals. 3 electron groups, 3 hybrid orbitals are necessary. So I take 3 atomic orbitals into hybridization. I take always an s orbital before a p orbital. Why? Because the s is lower in energy. So what we'll see is a p that's left over, and these 3 degenerate orbitals are called what made them? An s and 2 p's, sp2. I still put 1 electron in each. This energy difference is a small energy difference. We're going to see what's special about that leftover p orbital. It's an ugly way to write difference. So even though it looks like Hund's rule says we should go back and pair, no, we're still going to put 1 in each before we pair because the energy gap between the hybridized and the atomic orbital is very, very small. So with that sp2 hybridized molecule, what we want to be able to think about is that 3-electron group, the trigonal planar system, carbon being the example we just did, which was trigonal planar. If we had a nitrogen that had 3 electron groups and nitrogen was in the central atom, that's what we called trigonal bent. 120 degree bond angles, it's flat. What happened? Well, we only had to take 3 atomic orbitals into the 3 hybrid orbitals. Where is that unhybridized p orbital going to end up? The atom uses hybrid orbitals for the sigma bonds. These will be the 3 sigma bonds. The leftover is that 1 pi bond. Now, the non-hybridized or unhybridized p orbital is where we get the parallel overlap, the pi bond. Let's see a nice image here. For our hybrid orbitals, we'll see an image for our pi bond, our unhybridized p orbital, and then we'll go into merging them. Okay, so 1s, 2 p's. Notice that now we are at 33% s, 66 or 67% p. So we're looking a little bit smaller, a little bit bigger lobe here than the sp3. Same basic shape. It looks like a p orbital with an uneven lobe distribution. But that's how these would come together to make that trigonal planar idea and the 120-degree bond angles. Here's where we have our two different types of bonds. Again, the sigma bond is that direct overlap that we talked about earlier. The pi bond is the parallel overlap, now specifically between unhybridized p orbitals. A sigma bond can be unhybridized, like we had talked about with s's and p's, but they also could be hybrid to hybrid or hybrid to s orbital, etc. This is the direct overlap, which was what we called sigma. This is the parallel overlap, which we call pi. Remember, sigma is stronger. It's the holding hands relationship that you get in college. Parallel overlap, the pi, is the not holding hands. The hey, I see you, you're there. It's weaker. It's not going to be directly overlapping. Here's where we can start to see those two different types of bonds. Again, pi bond, hey, high school, I see you. Maybe we stand and talk for a little bit. Sigma bond, now we're actually holding hands. And we have that Venn diagram going on. So we can start to identify the two different types of bonding once we see a double bond. Now here's this molecule that we just did the Lewis structure and 3D shape for. CH2O. One of those bonds, let's make that smaller. One of those is going to be a sigma. Choose one. Doesn't matter which one. One of them, though, is going to be the pi. Whenever you see a double bond, one is that direct overlap right here. Direct overlap, very, very, very strong. That's going to be the carbon sp2 orbital with the oxygen p. Remember, outer atoms do not have to hybridize. They don't need to. Oxygen has 2 unpaired electrons, so it's good to make its 2 bonds as an outer atom. When we see that second bond occurring between carbon and oxygen, it can't exist in the middle. It can't exist as that direct overlap because remember, electrons repel each other. So if we're thinking about these 4 electrons trying to attract these 2 atoms together and make a double bond, what we have to be able to imagine is how are they spaced out so that they avoid the repulsion that electrons contain for each other, but maximize the attraction. So we'll always see the sigma bond directly in the center of the 2 nuclei. And the pi bond, I want us to imagine, is around on the top and the bottom. It's this around feature that makes the pi bond itself. Together, a sigma and a pi make what we call a double bond. Now, a couple of things about that double bond. We said before a double bond is stronger than a single bond. Well, that's because a single bond is simply just a sigma. A double bond is a sigma with a little icing on top, the pi bond. Now, even though the pi bonds are weaker than sigmas, they're additive in strength, meaning a sigma and a pi will always be more strong than just a plain old sigma. What we also see with these sigma bonds is if in a single bond we have free rotation around this one bond. This can rotate, right? Think about holding hands with someone or just yourself. You can do it with yourself too. There's that free rotation. You can kind of flip your hands back and forth, back and forth. When you have a double bond, there is restricted rotation because of this new bridge on top and the bridge on the bottom. You're locked in place. And so that's going to be something we'll see later on as well. All right, 2 electron groups. Let's continue on. We've done carbon dioxide before. Again, carbon brings 4 electrons to the table. Each of those oxygens brings 6 electrons to the table. So we're looking at 16 electrons. 2, 4, 6, 8, 10, 12, 14, 16. But carbon doesn't have its octet, so we're going to share. Again, share. And there's carbon dioxide. Now, when we look at this central carbon, again, we can look at its valence electrons in the 2s and the 2p and identify what do we need? Well, we only have 2 electron groups. We would have called this linear 180 degrees. I'm only going to take 2 atomic orbitals in order to hybridize into my 2 hybrid orbitals. My 2 p's get left over. These hybrids are going to be composed of an s and a p orbital, so therefore they're called sp. I'll have 2 sigma and 2 pi. Every first direct overlap is going to be a sigma. The leftovers, any extra overlap, will be a pi. Doesn't need to be to the same atom. So what we see is carbon has 1 sigma to each oxygen and 1 pi to each oxygen. And so we can look at that central atom carbon and identify he is sp hybridized and has 2 sigmas and 2 pi's. I like this example just to mirror the first one. It's an example where we have 2 central atoms, but it's a simple one, so we're going to try it together. Each carbon brings 4 electrons to the table. Each hydrogen brings 1, so we're at a total of 10 electrons. 2, 4, 6 go into bonding with those single bonds. 8, 10. We don't have enough to reach an octet for everyone, so what we should do instead is form a triple bond. This also is sp2 hybridized. Let's imagine this guy, or sp hybridized. Let's imagine this guy right here. He's got 2 sigmas. And remember, everything else is a pi. So he's got 2 pi's. Even though they belong to the same pair, 2 double bonds in carbon dioxide or a triple bond in C2H2 is going to be a central atom that is sp hybridized. So with sp hybridization, we see that linear shape, 2 electron groups, 2 atomic orbitals are needed to make 2 hybridized orbitals. And so we'll have 2 sigma bonds and 2 pi bonds along that central atom. That formation of the hybrid orbital is 50% s, 50% p. So we're starting to look a little bit more loby on that one side. But again, when they're put together, here's the central atom. I don't want you to think that this is a p orbital when they're put together. It's just that they are have the two lobes 180 degrees from each other. Wow. I like this picture because I think it helps emphasize the triple bond itself. So when we look at this triple bond, we see that purple in the middle is the sigma bond. It's the sigma direct overlap of the sp carbon to the other sp carbon. And then when we look at the pi's, notice how the pi overlap is perpendicular to each other. They're 90 degrees because one is a py and one is a pz. And notice also when we're identifying those bonds that are formed by the overlap, this is unhybridized, always for a pi. Excellent. Now, where do we get the expanded octets? When the expanded octets occur, it's because the atom is in the n equals 3 principal quantum number for its valence electrons. L can be 0, 1, or 2. So in n equals 3, we have S's, P's, and D's. What that means is we can take up to, in our valence electrons, let's think about for arsenic, we have the 3s, we have the 3p, and way up higher, we do have the 3d. Arsenic is in the third row. It has 3 3p electrons in its valence. Excuse me, 4. Third row and below, but this guy happens to be 4. And what we would need to understand why arsenic makes 5 single bonds is it takes the S's, the P's, and 1D in order to hybridize into 4 or 5 degenerate orbitals called sp3d. Count them up, 1, 2, 3, 4, 5. And that's where we can put in our electrons and make 5 degenerate bonds. Now, the d orbitals can be used to make pi bonds, but again, we won't really talk about those. Primarily where that comes into play with H2SO4, the sulfur. But again, we're going to primarily look at sigma bonds for those sp3d hybridized orbitals. So even though the d orbitals are empty, they're still available in the valence shell. So there we go. This would be for the 3 guys. If we have 6 electron groups, we need 6 atomic orbitals. We'll take an S, 3 P's, and 2 D's. That's where we get SF6. Again, d orbitals can be used to make pi bonds, but we're going to stick with just the sigma bonds. And there we would see. Take as many atomic orbitals as you need to make the hybrid orbitals based off what you see in the electron groups. So this chart, we should add in this last, or the last 2 columns. The hybridization gets put into this chart really to be able to say, if I know the number of electron groups, yes, I can take the VSEPR theory, electron geometry. Now I know the hybridization and I know the orbital shapes. So we're really adding to our previous chart there in chapter 5.